Okay, guys, I'll be starting off in 30 seconds. You can scan this for attendance within that time, or will be showing it again later. Okay, guys, we'll start off now. Okay, so I'm Radesh Chandaluru from Programming Club IITM. Today's topic is greedy algorithms. So, first of all, that might seem like a pretty weird name, but I'll explain to you why it's named greedy and all. So, yeah. Also, it seems that the QR code has reached its limit. We will share the link if that's the case. Don't worry about that. We will share it in the middle of the session if it's not working. So today's agenda is, first of all, we will talk about what greedy is basically. Then we'll see a basic problem on greedy. Uh, After that, I'll be telling you about sometimes why we can't use this algorithms. And then in the end, we'll see some more problems. So first of all, what is a greedy algorithm? So basically, in any competitive coding problem, uh, we basically have to find the solution for the whole thing. Basically, there is a big problem, and we have to find a solution to this, taking into account the whole problem. But in some problems, what we can do is we can think about just a part of the problem and make a decision, and based on that, we can build upon it and making those small choices that will lead us to the answer for the whole thing. So this is where we can use greedy algorithms. So basically, greedy algorithms make a locally optimal choice step by step in hope of finding the final optimal solution. So like at every point, it basically considers the best possible option without considering the consequences. So usually these type of algorithms are just derived by intuition mostly, and then we can prove them later on, but usually we just tell it by intuition, and you'll see what I mean when we see the problem. Yeah, so this is the problem. Basically, there will be n integers given, and we have to find uh, how many of these numbers can be chosen at max such that the sum of the selected numbers is less than or equal to a given integer m. So the test case would be like this. It would basically be like the first line contains an integer n, and then it contains an integer m, and then the next line contains n integers. Note that the integers don't have to be sorted, although here I have given them to be sorted. So here the greedy algorithm which we should apply is pretty simple. So here basically we just keep selecting the smallest number and add it to the total sum until the total sum is greater than 100. Basically, like we have to keep that total sum of the selected numbers less than 100 here. So we will just keep on adding the smallest numbers until it becomes more. And when it becomes more, we just exclude that last number and then be like, the selected numbers we have, that is the maximum number we can have. So why do you think that would be correct? Why should we select the smallest numbers? That is because basically like we want to select the maximum of these numbers such that the sum is less than 100. So like it is intuitively favorable to choose the smaller numbers, right? So that is why basically why we're selecting the smaller numbers. It is so that we can choose the most of them, like we can choose more. So here we would basically first choose 10 and then 10 and then 20 and then 30. Next, if we choose 40, the sum would exceed 100. So we do not choose it. So see, 10 plus 10 is 20, 20 to 20 plus 20 is 40, 40 plus 30 is 70. So the current sum is 70 if we choose the four smallest numbers. One second. And if we choose 40 after this, the sum would exceed 100. So we do not choose 40. So we can at max choose four numbers whose sum stays equal to or below 100. These are the four smallest numbers. So observe that for any other four numbers that we choose, that sum will be greater than or equal to 70. So this means that this is the smallest sum of four numbers possible. And this itself, this is less than 100. And if we add 40 to this, it would exceed 100. So we cannot choose five numbers. It's impossible. So this is one greedy algorithm. This is a greedy algorithm for the problem. Let's see how to code it. So this is the code for it. You cannot see the bottom part. One second. Okay, so basically first we define NNM, then we take the input of NNM. After that, we make the array for the n numbers. We take the input for all these numbers. After that, we sort all of these numbers so that the array becomes such that the smallest number is in the starting, largest number is the ending. And then we define max equal to 0. This max is basically the maximum number of integers that we can select. And the current sum is basically like before in the algorithm when you saw that we were adding 10 plus 10 and so on. We store the current sum in this. So basically, this is a loop. So basically, we loop from I equal to 0 until n minus 1 basically actually. This is basically the loop of all the numbers in the array. So if ai plus the current sum is less than equal to m, we will say that we can choose one more number. So we increment max. And when this condition fails, basically when the current sum is impending to go over m, then uh, we stop incrementing max. Okay. And then in the end, we just print max, and that will be the answer. So take a moment to digest what we did. This is a basic greedy algorithm. Okay, let us move on. So we can't always use greedy algorithms. They seem very, sometimes they seem like something amazing, but we can't always use any greedy algorithm that comes to our mind. So let's see some example or something. And yeah, so greedy algorithms are defined by intuition, so they might not always work. So let us see this example. So this is basically this is some structure. So in this structure, I want you to choose a path starting from 7 through different nodes such that the sum of values on the nodes is maximum. Here we might intuitively say some greedy algorithm. We might say that choose the largest value node at each step, but that won't work in this case. Observe that if we start at 7 and then we choose the largest node connected to it, we would go to 12. And then if we choose the largest node next, we would go to 6. 7 plus 12 plus 6. How much is that? That's 25. But clearly there is a larger path, 7 plus 3 plus 99. So here the greedy algorithm, which we derived from intuition, does not work. So any random greedy algorithm does not have to work. That is basically what I want to say. So whenever you're choosing a greedy algorithm, make sure that it would work, or prove that it would work, or at least be confident that it would work if you want to use it to solve the problem. Here it was easy to come up with a counterexample, and this is the counterexample which I showed you. So here we cannot just choose the largest value node at each step. So greedy algorithms don't always have to work. That is the main point. So let us see some more problems and discuss about them. So this is a problem. This is a G1 teleporters, 1791 G1. So in this problem, there are some points on number line. The points are labeled from 0 to n, and there is a teleporter located at the each point 1 to n. At some point I, you can do the following. You can either move left, it costs 1 coin. You can either move right, it costs 1 coin. Now, if you use a teleporter, one second. If you use a teleporter at point I, if it exists, it costs AI coins. And then you teleport to the point 0. Once you use a teleporter, you can't use it again. In total, you have C coins and you start at the point 0. The question is, what is the most number of teleporters that you can use? So the input contains multiple test cases. The first line is an integer t, number of test cases. The first line of each test case contains two integers, n and c. N is the length of the array, and c is the number of coins you have respectively. These n integers are a1 to an. These are the costs to use the teleporters at the points 1 to n. And it is guaranteed that the sum of n over all test cases does not exceed 2 in 10 power 5. We have to basically output the maximum number of teleporters that we can use. This is a nice problem. Think about how we can solve this. I'll give you about maybe 3 minutes to think about it. This is a good problem, so do think about it. We'll discuss it after that. Okay, guys. Uh, I'll start explaining now. These are some test cases, by the way. Let's look at the first one. Yeah, the first test case here is has total 10 test cases. The first test case. This first one is having 5 integers, and the sum should not exceed 6. So to get, let's say, like all of these costs are 1 basically, and it says the answer should be 2. Let's see why it's 2 and all. So to reach the first teleporter, we'll have to use 1 coin, and to use the teleporter itself, uh, we'll have to use 1 coin. So 2 coins are gone. Then we'll get back to the 0th position. Then the closest teleporter now is basically the second one. We will take 2 coins to reach that, and we will take 1 coin to use it. Now 5 coins are done. We cannot get to any other teleporter again. Basically, that's done. We can only use 2 teleporters uh, at max. You might be inclined to say that, uh, okay, so that's good. Let us just go to the closest teleporter that is available to us and use it. However, that would be a mistake because if you see, let's say the second example, uh, if you use the first teleporter, you'll have to basically use 101 coins, like to basically use it to get there. 1 coin plus 100, that's 101 coins. But to use the second teleporter, to get to the second teleporter, we only need 2 coins. But to use it, we need 52. So total we need 54. So in essence, to use the second teleporter, we need 54 coins. In essence, like to get there plus its usage, we need 54 coins. So I think some of you may understand where I'm going with this. And also in the question, there was another point. You can move left by 1 unit and it costs 1 coin. That is actually irrelevant to this question because it is not beneficial at all to move to the left. Because after you use any teleporter, you're coming to the 0th position again. So to go to a teleporter, you'll have to be going right. And if you come left again, it's like irrelevant to go right in the first place. I mean that uh, let's say that you're at the first position here. This is the 0th position. I mean, you're at the 0th position, and there are some teleporters here. Okay. So let's say you move here, and then let's say you move here. You have used 2 coins. Okay. Now let's say you move to the left, and now you will have used 3 coins. And now let's say you use this teleporter. So you have used 3 coins, you have got to the first position, and you have used the first teleporter. But don't you think moving forward and coming back is irrelevant? You're basically wasting 2 coins. So we will not even think about going left. That is irrelevant for us. So how would we do this problem? So we have discussed that in essence, to use any teleporter, we would have to travel to it and we would have to pay the price of the teleporter. For a teleporter at point I, the total cost to use it would be I plus AI. Now recall the first problem. This is now essentially the same thing. We have to choose the maximum number of teleporters without spending more than C coins. And the essential cost to use each teleporter is I plus AI. Okay. So if you see the first test case here in the input, to use the first teleporter, we would need 2 coins. To use the second teleporter, we would need 3 coins, then 4, then 5, then 6. For the second test case, to use the first teleporter, we would need 101 coins. For the second one, 54. For the third one, 16. For the fourth one, 10. For the fifth one, 9 plus 5, that is 14. So you get where I'm going. We have to choose the smallest of I plus AIs until we go over C. So this essentially became the first problem that we have discussed before, right? I hope that makes sense. And once you use a teleporter, you can't use it again. So that is the important point here. It basically means we can't select anything twice, or else if we as many times as we wanted, we would just select the one which had the least I plus AI value, right? That's not the case. We have to select each one only once, maximum once. So that is that. And 1 second. This is the code for the problem. I'll just discuss it at very briefly without going too much detail because we did a similar problem before. We basically take the input for NNM, then we make the array A, and then we're basically looping through it, and we take the input for A, J. J is going from 0 to n minus 1, and then also we add I to every AJ because we have to store the essential costs, not just the normal cost of using teleporter. So the I is equal to J plus 1 because when J is equal to 0, that's the first teleporter basically. So you have to add 1, not 0. So I is J plus 1 and we add I. Then we just sort it. And after that, it is very similar to before. We just go through everything. We just select the smallest costs and then we output the max. And that's that. There's this there is an error in this. The thing is that uh, you can't use int here for the sum because they mentioned that each cost can go until 10 power 9 and there are many integers. So I think we have to use a different data type, isn't it? What data type do you think that is? This is a pretty simple question. What data type do you think it is? You can just scan this and type your answer. I'll just give you 30 seconds to do this, and I'll tell you why I'm asking this question also. Okay, yeah, cool. It looks like most people are saying long int, and that is correct. This might seem like a trivial problem, and you might be thinking, why are you even asking this? But many times, what people do a mistake in such problems is that they just use int and they don't use long int. They basically forget or something I've done it many times. I've done this mistake, and then the submission goes wrong, and then I think for a long time, why is this not working? And after 1 or 2 hours, or after one day, I should just use long. So this is a common problem. So as this question, so you all will remember that uh, always read the constraints of the problem and make sure that your data type would work. So I would prefer always using long long. There is not a large time difference between int and long long. So instead of int, you can just use long long in every place if you want. That's a suggestion from my side. So that's why I asked you that. So this is one more easy problem. Uh, we'll try to do this pretty fast because there will be one more session after this on brute force. So hang in there. There are n block towers in a row, and the tower I has height AI. You're part of a building crew, and you want to make the buildings look as nice as possible. In a single day, you can perform the following operation: choose two indices I and j, and then move block from tower I to tower j. This essentially decreases AI by 1 and increases AJ by 1. So you think the ugliness of the buildings is the height difference between the tallest and shortest buildings. You want to find out what is the minimum possible ugliness you can achieve after any number of days. The first line contains one integer, the number of test cases. The first line of each test case is an integer n, the number of buildings. And the second line of the test case contains n space separated integers a1 to an, the heights of the buildings. For each test case, output a single integer, the minimum possible ugliness of the buildings after doing any number of operations. So I'll just give you 1 minute to think about this. This is a bit easier problem, I guess, and it doesn't require a big algorithm anyway. It is a pretty direct approach to this. So yeah, think about it for maybe 1 minute, and we'll discuss it. Okay, so I think that's enough. We'll just discuss it now. If you didn't get it, it's fine. So let's see one of the test cases here in this. Let's take this test case. Five integers are there: 1, 2, 3, 1, 5. So let us see what happens. We take this, and what do we want to do? We want to minimize the ugliness. So we will try to decrease difference between max and min. So what should we do? We should we can take one from the highest tower and put it in the smallest tower. So basically, we'll move one from here to here. So we'll get this, and then we will move one from 4 to 1 now. We'll get this. And once we get this, observe that whatever we do, there is no change. There is no change anymore. We can't do anything. And we can actually generalize that for any tower heights, we will reach a similar point. So all towers will be of the height x or x plus 1 height, after which there will essentially be no change. Okay. So in this case, the ugliness is 1. You know when the ugliness is 0. The ugliness would be 0 when at the end every tower has the same exact height. And if all n towers have the same exact height, what does that mean? It means that the total height is a multiple of n. And observe that the total height of all towers did not change in this whole operation. In all these operations, the total height is a constant. So when total height is divisible by n, then the ugliness that we can achieve is 0. Else it is 1. So that's basically it. That is the answer. The code for this is pretty simple. If just find the total sum of all the towers, and then you find the remainder. So basically, if the total sum modulus of n, if the remainder when total sum is divided by n is 0, then you output as 0. If the total sum divided by n gives a remainder, some remainder, then you just output 1. So the implementation of that is pretty easy. I hope you can do it. If you have any doubts, you can contact us. So that is it for the session on greedy. Now Mihir will take over. He will be giving a session on brute force. Thank you.
Okay, hello, am I audible?
Yeah, Mihir, we can hear you.
Okay. So we'll start in a minute. Is my screen visible?
Yeah, we can see the Slido link.
Okay, so basically this is the same Slido link which Radesh had. I'll be continuing it as well. So I'll just give you a few seconds to scan this and get to Slido in case you already haven't. Okay, fine. So we'll start now. Okay, so this session is about brute force. And basically what brute force is, it's basically you trying out every single possible combination. So suppose, say one of the very basic example of a brute force is in an array, you want to find the number 2, say the first occurrence of 2. And what will you do? You will go through, you'll start from the beginning and you'll keep going through the array until you find 2. Right? Because that's what you're doing. You're looking at every single possibility and seeing whether it's true or not. So let's start with an example. A grid of size n cross n has integer entries in every 1 by 1 cell in it. The power of any cell in the grid is the sum of entries of all of its neighbors. A neighbor of any cell is another cell which has common side with the said cell. Find the power of the most powerful cell. Okay, so basically what I'm asking is, say you have a grid. And you have elements 1, 2, 3, 4, so on. So in this case, power of this element will be 5. It will be 3 plus 2. The power of this element will also be 5. Similarly, this will be 5 and this also will be 5. So coincidentally, all powers are 5 in this case. So basically, your task is to find the most powerful cell. And like, I don't want any of you to like code this or something. Just take a look at it and think how you'll approach it. Like the approach is also very simple. It's kind of trivial only. All right, so I hope many of you got it, because like just think of the most simple approach you can come up with, and that's the answer. And I want to think, is there really an elegant method to do this? Like what I believe, like what most of the people will do, and that's the best method, that is approach each and every cell, calculate the power, and then among all the powers, find which one is the maximum power. Yeah, we don't really have a choice aside from going over all the cells. And here what we are essentially doing is we're essentially implementing an O(n) square algorithm, right? You have an n by n, and we go to every cell and calculate the power, and we don't have a choice from this. And this is sort of the idea that we'll be using on to solve other brute force questions. So yeah, that brings us to the concept brute force. This is basically a method to solve questions, to approach questions. Brute force is an approach to solve problems which involves going through all possible cases and selecting whichever one is most favorable. It can also be used to find all possible solutions. So yeah, we'll look at examples. We'll look at many examples in fact. Okay, so in the first example which we did, the one with the power of cell, we didn't really like use much mathematical elegance, right? We just we had a very simple approach. We had like a normal approach, just go to each cell and look at the value. And well, there is a clear drawback, as you can see. If the value of n is really large, then the O(n) square algorithm will lead us to time limit exceeder. So whenever you are implementing brute force, the first thing you need to look at are the constraints, right? You need to look at what value of n is given, what can you do with it and all. So we'll look at the example. Okay, so if you want, you can open this as well. Like you just have to Google code forces 122A and you'll reach the problem. So yeah. Okay, so can you all see the problem? If you can see the problem, just like react or do something. Okay, nice. All right, so I'll let you read the problem for a second. Okay, for a minute, I'll give you enough time. Like as I said, the first thing you need to look at are the constraints. So in this case, take a close look at what value of n is given and what can you do with it. Okay, so I hope you read it, and yeah, I'll go through it as well. Okay, so what we basically know is a lucky number is a number which basically is made up of 7s and 4s. So yeah, as they have shown, 47, 744, 4 are lucky, and these three unknowns are not. Then Petya calls a number almost lucky if it could be evenly divided by some lucky number. Help him find out if given number n is almost lucky. So yeah, by evenly divided, it means perfectly divisible. It's not that the quotient should be an even number or something like that. It just means perfectly divisible. And yeah, it gives you a number n between 1 and 1000, and you print yes or no. Okay, so if we take a look at the constraints, that's the first thing we should be doing. You see that n is less than 1000. So all numbers that can divide n will also be less than 1000, right? So what we have to do basically, we just need to take a look at all lucky numbers which are less than 1000, and we can actually just like write them down manually. So 4, 7 are lucky numbers. Then you have 44, 47. Then 74, 77. And you'll have 8 3-digit number like this. So 444, then you have 447. And so on, like I don't, I can list all, sure. So 474, 477, and basically just add a 4 here and just add a 7 here. So 7, 4, you add a 4, then again 7, 4, and you add a 7. That's the way to get. And similarly, you do for this as well. And now you'll have an array in which you're going to store all of these numbers. You'll have 4, you'll have 7. You can just literally type this array manually. So, and yeah, okay. So once you have this array of all lucky numbers less than 1000, then what you'll do is you will take the input. So you'll take n as an input, and then you'll go through this array, and you'll see whether any of the element from this array divides n. If any one of them divides n, then yes, answer is yes, we are done. And if none of them divide, then the answer is no. So here, because of the constraints, we can sort of do this question manually. So here you can see the code. So lucky numbers, I wrote down this array manually. All elements which are lucky and less than 1000, then basically I'll have this variable I, and I'm iterating this I less than 14 because size of this lucky number array is 14. And if if the loop breaks inside, it means that the value of I won't be 14. It will be, say, less some 5, 6, 13. Assume some random value where it breaks. And if I equals 14, it means that this entire loop has successfully run without anything breaking. It means that none of this lucky numbers divides n. So answer is no, else answer is yes. So that does this question. Yeah, so we wrote the possible lucky numbers manually and it worked as value of n is very small. But what to do if, say, value of n is really, really large? Like it's not possible to write all these lucky numbers manually. So yeah. I'll give you a minute to think what will you do in this case. So, well, I mean, we are done with the question. This is just more of an afterthought. So, well, if you look, the way we generated these numbers, say we have the 1-digit numbers 4 and 7, and we want to get the 2-digit lucky numbers. What we do is we write 4, and then in its units place we add 4 and 7. Then we write 7 in its unit place. We add 7 and 4 and 7. Now from 2 digits, suppose we have to go to 3 digits, then we have 4, 4. So what we'll do is we'll have 3 4s then. So 4, 4, 4. So we'll keep this from this 44. We'll keep the 44 just like that and add 4 and 7 in its unit place. And similar thing we did with 47, similar thing with 74. We kept 74 here. Then we added 4 and 7 in its unit place. So suppose for 10 raised to 6, what you can do is like you can try writing a recursive function. What it will essentially do is say this, we know that this has 2, this has 4, this has 8 elements, and the next one will have 16, the 4-digit one. Suppose you want the 4-digit one, so you'll go through this vector. So you make a vector of all lucky numbers till that point. You have this vector and you look at the last 8 numbers of that vector. And for every number you do that number into 10 plus 4, that number into 10 plus 7. So first one you'll get 444 into 10 plus 4. So this and 4447. And you push back both of these in the vector. So since you have had a session on vectors, you know different functions relating to vectors. So basically this is something like you can potentially do if the question was different. We won't code it because that's not what the question asked. Like we already solved the question, but this is sort of an afterthought. Like we should be able to do these things even when the value of n is large. Okay, fine. Okay, so yes, we'll do another example. So one thing we have learned so far is look at the constraints. In last example, value of n was small, less than 1000. So we were able to manage. So first thing, okay, second thing. Again, I'll let you read the question and sort of form an idea how you'll do it. We are basically doing brute force. So one thing you can, like one approach you potentially can be, what you do is you basically let the days keep on passing by. Like you have a loop, that loop sort of signifies the number of days. And you keep running that loop on and on and on until their number of socks becomes 0. So like another approach you can have is like you'll look at the value of n, you look at the value of m, and then you'll try to like somehow mathematically figure it out. But again, other approach is like you can run a while loop like this. So I'll give you a few minutes. Oh, is there some issue with the screen? Okay, it's visible now. Okay. It's okay. I'll wait so you can look at the problem. Okay, fine. Okay, so for this problem, I'll write the code from scratch, like so that you guys can look at the implementation and all. Well, let replit load for a while. I basically code here. You can use any, like you can do whatever you want, like use any ID to code. Okay, while that's loading, I'll sort of show you my idea. So what we'll be doing here is we know that initially we got n pair of socks, and for every mth day, so M2, M3, M4, M, and so on, we get another pair of socks. So +1, +1. And another thing that you need to note in the question is that the order matters. So basically, this one, she does it late in the evening so that Vasya cannot put on new pair of socks before the next day. So you have to put pair of socks in the morning, but you get the new pair of socks in the evening. So say you run out of socks on mth day, it means that it's basically over because you won't have anything to wear that morning. It is similar to that burnt out candle question. I'm not sure which one you're talking about, but okay, I guess like if you know, like if you have an idea how to do it, then it's nice. Okay, so okay, I'll now discuss it. So 3M, let's write this down for now. All right, so we know for sure that first n days we will have some sock to wear. And then after that, how much that will sort of depend on values of m and n, because even during the first n days, maybe there are some days that are divisible by m, and in that case, we get a sock. So, okay, so has this, okay, so yeah, okay, fine. The replit seems to be loading. Okay, nice. Fine. Okay, so how will we do this question? So first N and M, we take that as an input. So let me check the order first. Okay, N and M, and again, the constraints are small, right? Both of them are less than 100, so we can like kind of basically do whatever we want. Okay, now then again, we want to find out the number of days. So there will be a days variable, and basically this is what will our answer be. And also there will be soft pair. So, and its initial value is n because we know that initially the number of socks pair are n. And what I'm going to do is basically I'll have a infinite loop like this. And obviously there will be a break condition instead of it. So okay, on every day, we know that number of soft pairs reduces by 1. And we also know that if that day is divisible by m, then the number of soft pairs will increase by 1, or the days. Okay. All right. And another thing, if on that day, suppose the number of will run out of socks. So if sock pairs, if we run out of the socks on that day, then basically the loop ends. So we'll break the loop. And if nothing happens, so basically the day will end just at its end. We'll go to the next day. So days plus plus, and the end of it, what we'll do is we'll print the number of days because okay. And basically like this is the idea that I wanted to show you. Basically run a while loop until you meet the condition. Like in this case, we didn't really think what the time complexity will be. Right? We didn't think, okay, this is O of n, this is O of n square, nothing like that. Since we know that the constraints are small, we can basically run a loop like this until our conditions are met, and this sort of ensures if the number of sock pairs equals 0, then we break the loop. So this part ensures that we aren't basically stuck in an infinite loop. So I've already solved this question. So I've basically written the same code. So you can see, okay, oh, I use the exact same variable names. Okay, fine. Okay, so I think yeah, this is done. So any doubt in this so far? If you have any doubts, you can ask here, or maybe like some of you might be asking on Slido. I'll go and check there once. Okay, fine. So I take that as no doubt. So we'll move on. Okay, so what we did here is basically we went on continuing the loop until we ran out of socks. And well, this is like an idea. Like, so we'll have our conditions. Like generally, when you run a loop, like mostly I think you would have written for loops, right, rather than while loops. Like that's what happens in most of the questions. But okay, like this is another thing. This idea of running infinite loop. Like there is another question in the problem set which will be released later, and that also I've put a similar problem which uses a similar idea. Okay, so yeah, in this case, what we did is essentially we checked every day to see whether we will run out of sock pairs on that day or not. But it may not always be the best way. Suppose the value of n and m were really large, then there's a possibility of us running into a time limit exceeder. So yeah, this brings us to a question. Does brute force work always? I know since I'm asking this question, the answer is obviously no. So okay, as I said, when using brute force approach, we may end up writing some O n square or O n cube algorithms for which certain values of n may lead to time limit exceeding. In such a case, okay, so if you have an O n cube algorithm, you need to come up with some way to sort of reduce it to an O n square. You can't like let it exceed your time limit. Okay, so far we have seen two things. The first thing is we look at constraints, and if the constraints are small enough, we just type the values manually. Second, again, if the constraints are small enough, then we can basically do whatever we want. Like we can run like while one and loops like this. But what if constraints are large? That's our third point. Then we need to sort of optimize our brute force approach. So we can't just go on trying every single possibility and hope that it will work. We need to sort of like use some mathematical or logical idea. So okay, so in this question we'll see how to optimize our approaches. So the question is 189A. If you want, you can like Google this and go to it yourself as well. Okay, so I'll let you take a look at this. I'll wait for a few minutes to sort of give you enough time to come up with an idea. I will wait till 6:10. So if anyone of you want to like try and code this, you can go ahead. Okay, some of you aren't like trying to really code this, then you can at least try and come up with pseudocode. Like it's a step after like forming the logic. So you would have formed the logic. So like try and thinking of the exact lines you will put in your code. Okay, so I will discuss this. The question says is, first of all, we have a ribbon of length n, and we want to cut it into pieces such that each piece is either of length A, B, or C. And it is given in the question that at least one such cutting exists. So we don't have to worry about, invalid question and all of those things. So fine. Okay, so let's assume, let's take some length ABC. And let's assume that number of pieces of length A are X, number of pieces of length B are Y, and these are Z. Okay, so we know that AX plus BY plus CZ is equal to N. And what the question essentially, okay, this is N, not M. What the question essentially asks is they want us to find the maximum number of pieces. So X plus Y plus Z, because X, Y, Z are the number of pieces. So the maximum value of this. Oh, there was a visibility issue again. Okay, okay. So I'll quickly explain what I did. Basically, we have a total ribbon of length n, and we have sizes ABC, possible sizes in which we can cut the ribbon in, and XYZ. We can assume this to be the number of pieces of length A, length B, length C respectively. And we know this X plus BY plus CZ equals N. And what they want us to find is the max value of X plus Y plus Z. And in the question, it's given that all NABC, like all of these four variables, are less than equal to 4,000, I think. So I'll just quickly check. Yeah, 4,000 and greater than 1. So fine only. Okay, so how can we find this maximum value? So one of our brute force approaches is we just basically find each value of X that is possible, each value of Y, each value of Z, like all possible trios, X comma Y comma Z, and just find all of their sums and see which one is max, because like that's the typical brute force approach. And we'll do something similar, but we won't do just that. Like what we'll do is, like we'll use the idea, if we know the value of X and Y, then basically we can find the value of Z from this equation. So you don't have to run a loop for all three variables X, Y, and Z. You just have to run those for two, X and Y. And why is this significant? Well, from here, if you see what can be the maximum value of, not A is fixed. What can be the maximum value of X? If you see X cannot be greater than this. You see, floor of n by A, you cannot have a X greater than this. And similarly for Y, its maximum value is floor of n by B. And for Z, it's n by C. So if you suppose run some kind of triple nested loop, right? Like you check all values of X from 0 to X max, all values of Y from 0 to Y max, all values of Z from 0 to Z max. Will basically have something that is like O of n cube upon ABC. And in this case, if say n is 4000 and ABC are 1, then like your total number of operations, I think it's more than like 10 raised to 10. So you'll have an issue. However, if you only iterate through x and y, you'll basically have something of this sort, O n square upon AB. And for every x and y, you can essentially check whether the value of z you are getting is a perfect integer or not. Suppose you get x, y, and z, or you basically x and y you are choosing and you're looking at z. So you choose two integers. And if z coincidentally turns out to be an integer as well, then you basically know that you have a correct solution to this. And basically for all those three integer values, you'll look at their sum and you'll compare it to some maximum sum and so on. So basically what is normally done in ON cube, you can essentially do this idea in ON square. So okay, so here you take the input int max, so maximum value. So we'll be outputting this later and we'll be storing the maximum length in this. Okay, what I'm doing here is I'm running a nested for loop. The first for loop goes through the values of x. So basically I'm calling it I here. I goes from 0 to n by plus 1 and j goes from 0 to n by b plus 1. J is basically y in this case. And I'm trying out all possibilities for both of this. And for certain value of I and j, if this thing n minus I into a minus j into b. So this is basically c into z. If you look at that equation, n minus I into a minus j into b, this is actually c into z. C, yeah, z. Okay, fine. If this thing is greater than 0, because obviously for some values it may be less than 0. So if this is greater than 0 and it is divisible by c, it means that we have an integer value of z, which also means that we have a correct solution. So in that case, length is I plus j, and this thing here is basically the value of z, I plus j plus z. So x plus y plus z, you can think of it. And if this length is greater than maximum, then we set maximum to be that length. And so basically we check all of these lengths, and among them the maximum length will print out, which is what we want to do in the question. So, okay, any doubts regarding this? Okay, so I'll move on. Okay, as I discussed, so we basically optimized our approach in this question. So to avoid our time limit error. Okay, finally. So the last example. So finally, we have reached at the end, almost reached at the end of the session. And again, this is also a fairly simple question. So I'll give you a few minutes to look at it. So, okay, a quick rundown of what we have done till now. First thing we did is looked at constraints. If the value of n is like say small enough, we can just manually write the answers. If that's not the case, like if value of n is small, but we don't really have an opportunity to manually write all the, not answers, but manually write all the significant numbers, then what we'll do is basically run a loop until our condition is met. And in that case, we won't really care about how large our like the time complexity becomes O n square and all. If the n is small enough, then we can run loops like that. And say if we do encounter a time limit issue where we can clearly see that the value of n is large enough to cause an issue, then we have to find some way to optimize our algorithm. Like try to reduce the time complexity, maybe make it O n square or make it O n log n or something of the sort. So, okay, so try this question. Okay, so I hope you guys went through the question and like sort of got a faint idea how to do it. So basically, they have defined a proper fraction if and only if the numerator is smaller than denominator. And they call the fraction irreducible if numerator and denominator are co-prime. Basically, the GCD is 1. And what we're given is we know a plus b, we know the sum of numerator and denominator. And we're asked to find out the maximum proper irreducible fraction. So I'm going to output the numerator and denominator separately. So okay, we know. Okay, is my screen visible right now? Like if it's not, you can like say no or something in the chat. Yeah, right. So basically, we know numerator plus denominator sum is n. And we also know this thing that the numerator is lesser than the denominator. And that their GCD is equal to 1. And we want to find the maximum such combination that satisfies all three of these conditions. So obviously, one of our approaches can be we take all values of a from 0 to n and 1 to n and check. And similarly, all values of b from 1 to n and check. Somewhat often like an ON square algorithm, like that will be our first thought if we are strictly following a brute force based approach. Like we'll take some and take some b, first check this, then check this, then check this. But other thing we can do is we can simply iterate over a, and we don't even need to iterate for all from 1 to n. For every number, we don't need to iterate a. We can just check until basically n by 2, because we are already told that a will be less than b. So we'll just iterate all values of a, like from n by 2, and we'll reduce them, right? So suppose n is equals to 8, then we'll start 4 comma, then yeah, 4 comma 4, this won't work. Then we'll try 3 comma 5, and this works, so well, will be done. And since we are iterating from n by 2 and reducing the value of a, the first solution which we get, say 3 by 5. Then in this case, 3 by 5 is the largest answer that can possibly exist, because all other answers will have smaller value of a and bigger value of b. So this is the most optimal answer. So essentially, that's what we'll do. Okay, so I have written a separate GCD function, and this returns us the GCD of two numbers. I think like day before yesterday, you had a session where you studied Euclid's algorithm. So this is essentially that. Okay, here. So n minus 1 by 2, I think for even integers, n minus 1 by 2. So for if n equals to 8, we'll be starting with 3. And if for odd, so n equals to 7, we'll be starting with 3 as well. Okay, so basically, we can start with n by 2 as well. It won't make a difference in this case. And basically, GCD of a and n minus a, because we know that that's b. If GCD of a and b is 1. So this is a very similar loop to the first question. We have a, and I set the values of a. And if GCD at any point becomes 1, then we break, and we basically print out the values, because now we know what the values will be at that point. So yeah, this is the question. So okay, so yeah, attendance. We had some issues with attendance at the start, so you guys can scan this now. Yeah, you can calculate BS. You can I did with A, you can do with B, sure, no problem. So there are no issues with this attendance, right? So this QR code works well, right? Okay, I'm assuming it's all right. So I'll stay here for a minute. So if anyone has any doubt throughout the lecture, like any point, you can ask now. Yes, thank you. It was awesome for me too. Okay, then. Okay, so basically, there is another link which I need you to scan. So I'll show that in a minute. In the meantime, on Slido, I'll launch a poll. Basically, it's like a feedback poll. Just let me know, how did you think the session was? So I've launched it. I'll show you the Slido link. Okay, basically, yeah, just scan this link and you'll go to Slido. There you'll see a poll and yeah, let me know how the session was. Okay, now aside from this, so you can, I think the link which I showed a few seconds ago had some issue, so you can try this link as well for attendance. Okay, so I hope everyone, like those who attended the session, were able to mark their attendance. If anyone has an issue, you can like let me know right now. Okay, fine. So, and then, okay, I promise this is the last link. This is feedback link. So aside from Slido, this is another feedback. And this is for the whole session. So Rajesh took greedy and then I took brute force. So for the combined session overall, just let us know how the session was so we can, you know, learn from it. Okay, so does anyone have any doubt? or in general, do you want to say something about the session or anything? So you can say it right now, otherwise I'll end the meeting shortly. Okay, so I'll stop sharing now. Okay, so if no one has any issues, then you guys are free to leave. I'll stay here in case someone wants to say something, but otherwise, yeah, you can. Okay, then I'll end the meeting.